Welcome to a new era of molecular medicine, where we shift from reading the parts inventory to understanding the architecture of life. The easiest mistake in complex biology is the fragmentation error, confusing the part for the explanation. A list of variants is not a description of a system. And when we read genomic data as a list, we ignore the building. Architectures contain hierarchy, redundancy, and reserve, properties invisible to fragment-centered methods. Deterministic convergence is the reproducible emergence of stable interaction structures. It is what the system does, not a metaphysical claim, but an operational reality. For convergence to be examinable, execution must be deterministic. Identical inputs and settings must produce identical outputs, removing framework randomness from the observation. Convergence means the system returns repeatedly to preferred configurations. This preference reflects the underlying constraint landscape of the genomic data. We define these as structural families, configurations that share dominant contributors and interaction patterns, even when specific variant membership varies at the margin. This leads to the model of distributed constraint architecture, where phenotype-associated behavior depends on interacting sets of contributors within a satisfiable space. In this framework, the relevant unit of analysis is not the individual variant, but the configuration. Multiple configurations can satisfy the same biological constraints. Within these configurations, contribution weights are structured. Some variants are recurrent stabilizers, others are amplifiers, creating hierarchy even without a single point of failure. Architecture is revealed under load. Through the perturbation protocol, we exclude dominant variants to observe how the system responds. Reserve allows the system to absorb perturbation without overt change. It is the alternative configurations that maintain function despite the loss. Reconfiguration is the process where a system, challenged beyond its reserve, settles into a different but still coherent configuration. Collapse occurs when reserve is exhausted and reconfiguration can no longer maintain coherence. The system crosses a threshold into a weaker, qualitatively different regime. So consider the hematological domain. Baseline analysis identified a distributed configuration spanning multiple mechanistic layers of iron homeostasis. Excluding the regulatory layer actually produced higher fitness, revealing that the baseline was held in a locally preferred but globally suboptimal basin. Sequential exclusion revealed layered reserve, where the architecture accessed peripheral supports to maintain perfect discrimination through 4 levels of perturbation. Between the 6th and 8th exclusions, we identified the collapse boundary, the finite limit of the original architecture's resilience in this cohort. Now, for drug discovery, this solves the target fragility problem. A target that is visible but not decisive will produce limited benefit, regardless of compound design. Architectural analysis distinguishes visible targets from decisive ones. We prioritize targets that are necessary across many perturbation conditions, deep within the reserve structure. Now, for drug discovery, this solves the target fragility problem. A target that is visible but not decisive will produce limited benefit, regardless of compound design. In the clinic, patients are stratified by their underlying architecture. 2 patients with the same diagnosis may require different interventions based on their specific attractor family. Biology makes sense at the level of architecture. NomosLogic, deterministic, exact, yours.